Okay, so hey everyone. Today and tomorrow we are going to learn how to build Google Gamma 4 from scratch. And in order to do that, I have prepared four Google Colab these playbooks. So I will tell you what is the difference between all of these. But let me first share it with you guys. I already shared some of these with you. So let me ping you guys one more time over here. So this one, I run it on A100 GPU. Then there is this one, which I have created on T4 GPU. T4 GPU. There is even one more, which I have created it on the MacBook. And we are going to discuss about all these things, like why are it's always being done. And yesterday, like the model that we are going to build today and tomorrow is of 35 million parameter. But even I am able to uh, trim it down to 20 million parameter. So I will say gamma. Let me add these folks. So gamma 20 million parameter. So we are going to learn. My voice is not audible. It's only for Gaurav or for everyone. Are you guys able to hear me?
Yes, Prashant.
Okay. Then it may be issue from your end, Gaurav. Okay. So I mean, we are going to start. I mean, all these run these Google Colab or the code, they're exactly the same, but they are little bit of modification. So, for example, this A100 GPU, and I'm just giving you the brief idea. We are all going to look at all of these in depth. This A100 GPU provides a high amount of a VRAM. So that's why there are some optimization that I have done on the top of it, like the block size, which is be higher in this case. Whereas the T4 GPU, it provides the lower, like only 16 GB of VRAM. So I reduce the block size in that case. For MacBook, you know that the MacBook does not provide the CUDA drivers. So in that case, we need to use something called MPS. So that is the optimization that I have done. And finally, I have built it on this Gamma 4, sorry, on this H100 GPU, which is the most expensive one. My training is even finished within an hour, but it is an expensive solution. But I did some optimization, and if you're going to look at the end, the results are not great because I trimmed it down to so much of a lower level. So we are going to discuss about all these things, like what exactly it's this is all about. Just one last thing, if you are going to look at this run book or this playbook, it has close to like 16 steps. Okay, this final inference step, 16 step. So my target for today that at least we will be able to finish these 7 steps up to this transformer block. And what exactly we are going to build in next 2 days is this architecture. We are going to build this architecture step by step. And that is what is the difference between what is present in the market right now, that they are giving you the black box. So in next 2 days, we are going to unfold that black box step by step to see how it works. So all of you guys who is with me from the last 1 month, we have talked about all these concepts, but I'm going to assume that you do not understand anything. We are going to look at all these things one by one, which is a good revision for you guys also. And on the top of that, you may get a chance to learn something new. So this is the architecture we are going to build. And just want to give you the high level overview of this architecture. So let me do this. So we will start with, if you are going to look at this run book, we will first start with the tokenizer step. And what tokenizer is all about is converting the text into something called token ID. Okay, and we are going to discuss about that. So we are basically going to convert the text into token ID because under the hood, all these LLMs, they are nothing but they are the deep neural network. So the thing they understand is something called a token ID. So that's why we are going to convert it into a token ID. Once that been converted into token ID, what we are going to do, we are going to define some of the model specific configuration. And we are going to discuss about what are these model specific configurations are. Next, once we are done with that, we are going to define something called rotary position encoding. So the text we are going to send to a large language model, we are going to send it in parallel. So we need to define the position where exactly the each token lies. So initially there was something called positional encoding. They were also called integer position encoding, sinusoidal position encoding. But if you look at the most of the modern model LMs that are built, they build across this rotary position encoding. So we are going to look at that. What exactly is that? Then we are going to do something called RMS norm or root mean square normalization. So basically the main idea is that the gradients which is been calculated as a part of the training, and all of you guys who don't understand gradient, I'm going to explain to you guys that we want to normalize it, that we don't want these value to become either too big or too large, too big or too small, because there is a problem called vanishing gradient or exploding gradient. We want to eliminate those things. So that's why we are going to use RMS norm. And if you are going to check this thing, the architecture diagram, Google team itself use RMS norms at many places. So we are going to discuss about that, why they use it at these many places. Once we are done with that, we need to define the attention mechanism. And most of the model providers nowadays, except for few of the Chinese model like DeepSeek or Kimi-K2, they stick to something called group query attention. So we are going to discuss that, what exactly the group query attention. And on the top of that, Google has done a lot of improvement to increase the context size. So there is something called sliding attention. There's something called KV cache. Not exactly KV cache, KV cache sharing. And there's something called PLE, which is called per layer embedding. We are going to discuss all those things in this layer itself. Once we define the attention mechanism, the next step is called something called feed forward layer. So one of the other aim of this workshop also, that when I'm talking about the 35 million parameter model, how we come up to that number. So we are even going to discuss about that, like how we come up to that number. And just to give you the hint, this is again one of the interview question where which layer of the large language model has the maximum number of parameter. So feed forward is a layer. We are going to see what exactly is that. And we are going to use some kind of an activation function, which is called gig loop. So what is the use of that? That is basically to introduce a non-linearity for your data set. Once we are done with them, we are going to use a transformer block. And this is nothing but whatever we have discussed so far, like RMS norm, this attention mechanism, there's something called shortcut connection. We are going to discuss about that. Then this feed forward network, we are just going to combine each of all these things. So that is going to create our transformer block. So, I mean, we just need to assemble all these things to create the transformer block. So my idea is by the end of today, we at least finish this transformer block. Once we are done with that, we are going to create this gamma 4 models. Again, this is a kind of an assembly, like whatever we have discussed so far, we are just going to assemble these part, and all these part, just to combine everything to create the model. So this is a simple thing. Next, once we are done with that, the step 8, the next step is, I mean, this one I'm going to discuss in the extreme end by the end of tomorrow, because here we are going to calculate like how we come up to this 37 million parameter. So here I have written this code, but I'm going to tell you the step by step. Like this layer, these many numbers of parameters is consumed. In this layer, these many number of parameters is consumed. This is a simple formula, but I'm going to show you like a handwritten kind of a calculation, how we come up to this number of 37 million parameter. Forget about step 10. Then we need to define some of these other parameters. So the first one we have defined is to define the model. These are specific to training. Like we need to train our model with the data set. And I think I have not talked about the data set. This is the data set we are going to use. Let me ping you this. So this data set has 2.1 million stories. We are going to train our model with this data set. And at the same time, it has like 22K validation row. So this is not at all a toy data set. This is a big data set that we are going to use to train our model. So we are going to train the model, but at the time of the training itself, we are going to validate it also. So this is a data set which the model have not seen. So we are going to see how our model is behaving at that point of a time. So that is the part of the validation data set. And we have close to like 22K rows. to test it out. Once we are done with that, define the training, we are going to define something called a batch and load estimation function. So the way LLM works is that we have the input pair and target pair. So basically, what LLM does, it generates one token at a time. So at the time of the training itself, we are going to provide him the data set where we have the, like, this is the input token and this is the output token. So during the training itself, we are going to train the model like the way we are going to expect the output out of it. That is the use of this part of the code. This is one of the most important part, is the calculation of loss. The same thing we are going to do with this validation data set to see how our model is performing. This validation data set, this one. So we are going to discuss about, we are going to use something called cross entropy loss to calculate this loss. Then we are going to use something called optimizer, and AdamW is one of the most popular optimizer nowadays. Most of the model, they stick to AdamW. There is one called Muon, which is used by Kimi K2. Except for that, rest of the world, they are using this AdamW. And what is the use of this AdamW optimizer is that when we are doing the validation and the loss is calculated, who is going to reduce that loss? That is the work of the optimizer. So we are going to see how to apply this optimizer. Actually, it's pretty simple. Tosh provide a function or a method to apply that optimizer. So we are going to see how to apply it. Then we start our training. We are going to save the model. We are going to see how exactly, I mean, this is just one step, which is called model.train. We are going to apply it. We will perform the training. Then in the loss function, we are going to save all those things like the training loss and a validation loss, and we are going to plot it out. And you see that here the green curve is the training loss, and the red curve is the validation loss. And at the start, some of you guys understand that when we initialize the neural network, we are going to initialize the weights and biases randomly. But as the training progress, as the optimizer is going to update all these weights, this need to be reduced. If this is not reducing, then our model is not learning. So we are going to see what exactly is those steps. And once we are done with that, this is the final step where we are going to utilize the existing model to generate these stories. For example, you see that it created this beautiful story based on the data that we have trained with. I will pause here for a minute. Any questions so far? Like, the ultimate goal is by the end of tomorrow, we have this working model up and running, following these 16 steps. And the main idea for today is at least we will reach to the step number 7. Again, I set up this class for 2 hours, but expect it to spill over to like 2.5 hours or 3 hours. So just be prepared for that. Any question before we start with the step number 1?
Hello, Prashant sir. So my question is, we are training the model for our basic knowledge. Means we have created our knowledge and we train the model from the start, right?
Mhm.
But I want to understand, like, this is a story based, the data which we are using.
Mhm.
But if you explain us how to create the, if the data is from company side in different ways, how do we make the data to train the model? Like, if you explain something about it.
Yeah, so I think I have told you guys that's a completely a different dedicated team within the company who perform that step. And most of the folks, they don't start from, I mean, most of the folks, they start with the step where the data is available. I can ping you. I think I ping you guys one of the training perform. Okay, let me search for that. Because if we start with doing the data filtering and all those things, that will itself is the big task by itself.
But I just want to understand that how do we process the data? Means what are the things which we need to be required to understand and create the data? For example, I just give an example, like there is a patching activity on Linux servers, right? So
Mhm.
there is a change request for that. So partially we have already raised that change request and done the patching activities and all. But now in future, if we are doing the patching activity, and after the patching activity, what are the changes has been happened to the servers, we need to create kind of testing case for that. So how do we train like this? Means we how do we collect the data? Means I need to understand like in this way.
In collection of data, that part you guys need to figure it out, like within your company. In terms of training the model, that part I can help you. But in that case, I don't think so. You need to train the model for that specific use case, because that will be a pretty expensive process. You may figure out that kind of a problem using either using RAG, or you can do the fine tuning on the top of it. I'm looking for that run book where we have, or let me ping you during the break. Uh, so if you don't mind, I can ping you. There's one course in the deep learning playbook where they show us like how to. Let me see. Yeah, this is the pre-training one. So this is one of the good course which is available on the internet where they showed how to collect the data and how to like do the filtering, like how to remove the duplication out of it. So how to like basic idea is how to make it training ready. So let me ping you guys this one. But just to tell you, that is a field in itself. And what most of the company they are doing, like for example, I can show you Meta Nama paper. Where is that? Not this one. Then I don't think so. This is the one also. Okay. This one. Yes. So what most of the folks they are doing, this the common crawl, they have already crawled the internet. This I'm talking the broad sense what most of the company they are doing, and they are crawling it every month. So this is the data set for the month of April. Oh, this is the month for the January, but they're already crawling this data set. So either you can use this unfiltered data set, or you can go to the Hugging Face, search for the common crawl data set, and look for these data sets. This in case if you want to build it from absolutely scratch. But for example, these Meta guys, they have told in this paper itself that it took them 16,000 GPU to utilize this entire data set. And that will cost you like close to 450 to $500 million just for training purpose. So it's a pretty expensive process.
I guess over here, Prashant, you're using stories, right? You said 20,000 stories. But
Mhm.
what is in the
Not
corporate
20,000,
world?
2.1 million.
Okay, yeah, in the corporate world, it's more like audit logs, change requests, more DevOps related. That's the data we're looking at, right? This example you're giving is crawling the web, internet, and all that stuff. But I think what he was referring to, probably Gaurav, was more like DevOps data and those sort of data, if I'm not mistaken.
Yeah. So for in those cases, I don't think so. You need to build the model from scratch. What you can do, either you can utilize a RAG, or you can utilize some kind of a fine tuning on the top of the model. Okay. We have lot of things to cover, but all those things which I'm going to tell you that apply to any data set that you can utilize. So all these concepts to build the model, like from if you want to build it from the ground up, maybe you will never ever get a chance to build this from the scratch. And again, like all these steps, we are going to define it today. In most of the cases, most of the company they are using some kind of a framework to build it. So you may not need to know about all these steps. These are all under the hood thing. What happened? Okay. So let's start with our first step, which is called tokenization. Not this one, this tokenization. So I think most of you guys are aware of tokenization, but here I have done some more optimization on the top of it. And the reason for doing all these optimization because I want this model to be trained on smallest GPU as possible. So like I showed you guys, I started with this A100, then I have done some optimization. I'm able to run this even on T4 GPU. Will run this means trained it on T4 GPU. With the help of these optimization technique, I'm even able to run it on Mac. And then I switch to one higher GPU also, which is the H100. So I'm going to show you what are those optimization techniques. But let's start with the first step, which is called tokenizer or tokenization. So tokenization in the simplest sentence, in the simplest word, is to breaking the sentence into token. So if this is a sentence, we are going to break it into tokens with a token ID of like this, and this. And the main idea behind that, because the LM, it does not understand the text. Because they are the deep neural network, we need to provide the token ID. And that is what we are going to do it over here. Like this is one token ID, this is one token ID, this is one token ID. So if you look at this, this is the code. So here I am using this tick token library. And what I am doing, I am saying it over here, use this GPT-2 tokenizer. So GPT-2 is one popular tokenizer which has the vocab size of 50,256 words. And they are mainly for English. So what is my use case is that I need to generate the stories which is in English language. So this is one of the perfect tokenizer. I was trying to look for tokenizer which is lower in terms of the number of the tokens or the word which is present. This is the best I can find, figure it out. Later on, I built my own tokenizer from scratch. So I'm going to show you how to build it. But just to understand that, I started with this GPT-2 tokenizer, which has a token, which has the length or the word size or the token size of 50257. With 50257 means, so let's say if I use this sentence itself, it breaks everything into one token in the simplest word. This is one token, this is one token, this is one token, this is one token. And under the hood, it has the token ID mapped to it. Again, let me take some random number, let's say 20, 300, 450, so on and so forth. But I mean, this is oversimplified explanation. Actually, this is a subword tokenizer. So it break the text into further. So this building, maybe this build is one token, ing is other token. So that is what happening under the hood. And the main idea behind that, to eliminate unknown token problem or unknown word problem. And that is the main idea behind this subword tokenization. Okay. So we started with this tokenizer, and the idea is that we are going to take the text, and with text means all these 2.1 million stories that we have seen, it's somewhere, this one, and we are going to convert into IDs, right? So basically, for example, if this is a sentence, we are going to break it into these ID. And on the top of it, we are going to calculate its length also. So for example, in this case, its length is 3. And just wait for a few more minutes. I'm going to tell you why exactly I'm calculating the length, because I want to see. Okay, let's forget about the length part right now. Just think of it that at this point of time, this is one of my function, and the main idea is to take the text and break it into token or the token ID. Okay. The next part is to prepare the data set. In order to prepare the data set, again, I'm going to use one function from the Hugging Face, which what it is going to do, it is going to create these, it is going to download this data set from the Hugging Face itself. So this line itself, ds equal to load data set, what it is doing, it is just downloading that data set from the Hugging Face. So far, so good. We have not done anything. What we have done, we converted the text into token ID and we just downloaded this data set. That's it. Now, this is the important part, which I was talking about, the optimization part. So again, if we go back to this data set, I told you that there are two parts of this data set. One is the train and one is the validation. Okay. So I have done some optimization. And again, all these optimization that I'm going to tell you is just, it's not mandatory. It's just all are optional. Now, what are those optimizations are? So once we converted these text to token ID, I'm creating two files. One is called train.bin and second is called validation.bin. And the main idea behind that, because what normally happens that once we use the tokenizer and we converted this text to token ID, we basically saves this token ID into RAM, or the more precise word of this, that is called VRAM, virtual RAM, which is the GPU RAM, right? And we all know that GPU RAM is limited. So I have two options, either whatever the conversion I'm doing for this 2.1 million stories and 22 rows for the validation, I can save it into the RAM. But that will be the huge amount of a RAM that is being occupied by my tokenizer. Or the other thing I can do is to save it into the disk. And save it into the disk in the form of a file, which is a binary file. And I am not going to read that file in a one go. Like all those 2.1 million plus 22 million story, I'm not going 22K story. I'm not going to read into one go. I'm going to read it in batches. And that I'm going to define what is that batch sizes. But the idea is I'm going to save it, all those token ID into a disk rather than keeping it to the memory. Well, is this is going to be the fully optimized process? No. But the whole idea is that I should be able to finish the training in the lower GPU also. I don't need a higher GPU to finish the training. And I have seen the difference between the two approach. I'm just giving you some number. So let's say if my training is going to take like 6.5 hours, if I'm going to keep everything on a GPU RAM, in case of if I'm putting it on disk, it's going to take 7 or 7.5 hours. That is the only difference. But the main idea is that it is an optimized solution which can even run on the lower end GPU like T4 also, or even on the Mac also. So whatever I'm going to tell you now is these are the optimization step which runs on the top of, just to make sure that our model or all the tokens will be able to be consumed or will be able to run on the lower end GPU. Is this part is clear to everyone? Any doubt? Okay. So here you can see, I'm just checking if the train.bin file is present or not. And if it's there, we are not going to create it. But here is the important part, that this is provided by the Hugging Face itself. So we have loaded this data set. We are using this process function, which we have defined it earlier, which is going to convert all of my text into token ID. And next, if you see the remove column equal to text. So if you go back to the data set, you can see that all these columns have this heading of text, right? So we don't want this. My main idea is that all these text need to be converted into token ID. I don't need this column name. So that is the main idea that I'm doing it over here, that I'm removing that column name on the top of it, which is the name of text. I'm providing some description and the number of process. So what this is going to do, that it is going to remove the column heading from the top, and it is going to call this function, which is the process function, and it is going to take all the story and convert into a token ID. That is the first step it is going to do. And I am running this process in parallel of 8. Next, what we are going to do, we are going to run over this tokenized thing, tokenize.item. And what tokenize.item is going to do, it's going to create the two set for us. One is for training and one is for validation, because in our data set, we have the two splits. One is the train and validation. So same way it's going to create, like this for loop is going to run, like one time it's going to run for train data set and one time it's going to run on the validation data set. That's what it's going to do. It's going to create two files, one for training, one for validation. Now, this is the most important step, which is called np.mmap, which is the memory mapping. This is the stage where I'm going to create that file which have all the token ID to it. And this is going to save the data to my disk, not to my to my RAM or the VRAM. And again, I'm telling you, these are all the optional steps. If you don't want to do that, if you have a sufficient amount of a GPU RAM, you can have all these tokens running on your GPU itself or the GPU VRAM. This is just for the as a part of the optimization. Next, what I am trying to do it over here, just pause for this length part that, okay, sorry. Before that, there's something called TQDM. What this TQDM is going to do is just going to show me the progress bar. So if you go here, okay, I am not doing this over here, but it's just going to show you the progress bar. Let me show you this thing. Where's that? That this progress bar is just going to show you how much is the splitting of the data happened, or how much the data is being converted to token ID, like 1%, 2%, all those things. Now, that's what I told you, that what we are going to do, that we are going to write those tokens not as a whole. We are going to write it in the batches of 1024. Same thing we are going to do when we are going to read these batches. Like, again, remember that we are doing all these as a part of our training. This is nothing to do with the inference part. Inference means once the model is ready and it is ready to serve to the customer. This is all we are doing to optimize our training. So what we are doing it over here, we are writing all those token ID into a batch of 1024. Same thing we are going to do when we are going to read that data set back for the purpose of our training. And we are going to use something called air.flush. So this flush functions comes from the Linux itself, right? In the case of Linux, what we are used to do, that we are flushing the data. So all the data which is present on the RAM, we want to save it into a disk so that we can utilize it all for the future purpose, right? So that any data will not be lost. So the main key takeaway from here, that we are going to take this text, we are going to convert into token ID. We are going to calculate the length also. Like for example, in this case, we have the 3 token. Again, I am not talking about length part, which I'm going to talk later. But at the end of this loop, what it is going to happen, that you have the big array of multiple token ID. Like for example, this big array. So we are going to write this big array in the form of 1024 batches. And same thing we are going to do on the retriever stage, that we are going to read 1024 batches of token at a time. Any doubt so far? Anything which is not clear? It's a simple process we are doing. We are just converting the text into something called token ID. And the only other thing which we have added is we have done the optimization so that we can run this on a lower end GPU or CPU. Anything which is not clear to you guys so far? Yes, no? Okay. So when I was building this solution, I felt that this 50257 token or the vocabulary size for this kind of a scenario is pretty big, because my ultimate goal is to generate the stories, right? And 50257, which is the vocab size for this GPT token, is a kind of an overkill for it. On the top of that, when we are going to use this model for inference purpose, like once this model is built and I'm going to use this model, what exactly is going to happen? Like if this is my vocabulary size, this going to be multiplied to the dimension size. And that much amount of a VRAM is going to be occupied in my memory. Okay. And this, I feel like, let's say this is 384. So this much amount of a token or VRAM is going to be utilized. And on the top of this, this is going to count in my parameter size also. So this 50257 into 384, let's say, just for sake of discussion, if this is a dimension size, and all those of you guys who don't understand dimension, we are going to talk about that. This is going to be the count as a parameter size. So what I have done, let me ping you this script. what I have done, rather than using this GPT-2 tokenizer, I have built my own tokenizer. And what exactly is done in this script? Again, this is out of the scope of this workshop, but the main idea behind that is take this story by itself and use those story to create the token ID. So it is exactly going to do the same steps, that it is going to read the data from this stories, tiny story, and convert into a token ID or the subword based tokenization. So let me show you how this look like, or let me show you what exactly is going to happen. So if you are going to run this script, what it is going to happen, it's going to create 4 files. So one is called tiny tokenizer.model file. This is the file. Like if you look at this first code, we are using this line piece of a code, which is basically downloading this tokenizer and utilizing it. Same thing we are doing it over here, that it is going to down, like we are going, the script itself is going to create that tokenizer file. It's going to create one more file, which is a kind of a human readable one. And on the top of that, it is going to create this train.bin and validation.bin. All the logic is already embedded inside the script. So let me show you how this tokenizer, that this vocab file look like. Where is that? Let me show you here. That somehow, I mean, I just came up with some random number and I restricted it to the 8,000 token. And under the hood, you will see that this is how the split look like. That it breaks it into this token and this token ID. That's it. Only, again, is it going to solve all the issues? No. The main idea is to make it specific to this story itself, this tiny story. So this is only going to work in this use case itself. It's not going to work anywhere else. For all of the rest of the scenario, if you are training it with any other amount of a data, try to use this GPT-2 specific model, tokenizer, sorry, this one. But in this use case, because I'm using the same data set to train my tokenizer, this is going to work perfectly in this use case. Krishna, you are on mute if you are talking.
So, Prashant, so you are thinking in the terms of parameters, right? So you are very conservative about uh, using the parameters because you want to save some resources and you don't want it to get expensive. So are you validating the parameter size at every level, like encoding stuff and also the processing, preparing data stuff?
So I have a dedicated section for you guys, which I'm going to discuss it tomorrow, because I need to tell you a lot of other thing, which is called this parameter calculation.
Okay.
So here we are going to see each and every step.
Okay.
And yeah, that point is right. So let me ping you guys one more blog. And yeah, Sharuz, we will come to your
Because
question.
the reason you went from that GP2 to the other tokenization is just because you want to be conservative about the parameters that you are using, right? The optimization.
Parameters, on the top of that, I want this model to be run on the lower end GPU.
Right.
So if you look at this gamma model, which is been released by Google, if you look at the lowest model they have created, it is based on 2 billion parameter. Then there is something called 4 billion, then 31 billion, then 26 billion. So I want a model which has been as low end as possible.
Right. So the parameters, they translate to VRAM and then they translate to expense, and the
Yes.
way that you want to use a GPU, everything is in coherence, right? So from the model that you want to, I mean, the numbers, the number of parameters that you want to use to till the expense that you want to uh, minimize.
Yes. That, I mean, that's what I told you. These are all the optional steps which I have done just for the optimization purpose. So you don't need to do these. Sorry, I'm just replying to this guy. Yeah, so you are correct, Krishna.
Yeah, it's all depend upon what I mean amount of underlying hardware that you have to build the model.
Exactly. And that's what even I have a dedicated section for you guys tomorrow. One is this parameter calculation where we are going to know that how I come up. I mean, when I'm talking about 35 million parameter, at which and every stage where exactly that parameter is being occupied. Secondly, we are going to do the calculation which is called the memory calculation. Like if your company will ask you that you need to run this 35 million parameter model or 1 billion parameter model, how you are going to perform that calculation. So we have a dedicated section where we're going to see that.
So that I mean we can justify that if you want us to build a model, we
Mhm.
need at least this much of hardware.
Yes, yes, that's
And
the whole idea.
yeah, and my one question is that is this approach will be for it's a common approach that can be used to build all the models, or it is specific that for just for these stories it's just an example.
No, so this is going to work for all the models. Only thing is like this Google Gamma architecture, this attention mechanism, they have added some more thing just to increase the context length. So those are all the other advantages or the things which is added by Google, but this model is going to work for all the use cases. I mean, this is specific to like the data set, but if you have the different kind of a data set and if you have the hardware, you will be use the same concept for training any kind of a data set or any model you will build using it.
Okay, so this is a common. This is not
Yeah.
specific to this store. Okay.
So Prashant, one question. So if you wanted to train the private data, okay, you
Mhm.
don't need the entire GP2 vocabulary size. Okay,
Yes.
that's the reason you are building your own models to reduce the token. Because if you know if your private data, for example, if you take any Jenkins file, right, or else any
Exactly.
standard commands, right? Okay,
Yes.
so you can reduce the number of tokens because your data, private data is fixed. So you are
Exactly.
coming up with your own model. So that way, right, it will run on any machine. That's the whole
Not own model, own tokenizer.
own tokenizer. Okay, own tokenizer, which takes a lot of time for training.
No, this tokenizer is just going to build like I am. If you look at
Tokens.
this code itself, I'm building it only for 8,000 vocab.
Only 8,000. Correct.
So
Got it.
I took those stories. So even I have not took all the stories because I want this to be as simple as possible. So I took first 500 case stories. I run it on the top of it. Now the question is, what will be the case if that word is not present in this 8,000 word? So that is the main idea behind this subword tokenizer, that it's going to break the word into sub token. In the end, if it's still not able to figure it out, it will say something called unknown word. So that is the risk that I'm taking, because in GPT-2 you are not going to see those kind GPT-2 tokenizer. One more thing I want to show you guys, sorry, before I'm going to answer your question, is this is one of the most popular app. And if you see over here, there are a bunch of other tokenizer which are present, like this O200, O2 200K base. This has been used by GPT-4 OSs. There are other bunch of tokenizer. The main idea behind that, for example, let's say the Quen one, Quen tokenizer. It has a vocab size of 162K tokens. So there is never been a problem of unknown token. But in Quen, you have the multilingual capability, that it even has the Chinese language, it even have the Indian language, it even has the some of the European language like French and German. This use case, I know that I'm building only for the English language. So again, in those cases, it's this 162K is a kind of an overkill. So what you have mentioned is absolutely correct. Is like, you need to know your use case, and then you can choose the tokenizer. If you don't want to take any kind of a hassle or you don't want to take any pain, just start with the Quen tokenizer. It's going to fit all of your use case. If you think that it's going to you need to tackle the English non-English kind of a use case. But if your use case is just English, just start with the GPT tokenizer. It can satisfy all of your requirements.
Okay, so if I understand correctly, the tokenizer will not take much time, but that when you use this model at the time of training, it will take too much time to train the model. Am I correct? When you say 7 hours, 5 hours, you said, right?
Those are all the different steps. So tokenizer is one of the part. There
Very
are
first.
other steps which is been involved, which is going to take time, which we are going to see in next,
Correct.
today and tomorrow.
Yes, yes. Got it. Got it. Thanks.
I think there's one more person who has a question.
I just wanted to ask about the vocab size. So we go from 50,000 to 8,000, and that explains. I was just curious about the number of the size of the vocab
Okay,
in the two.
sure. That's what I said. I am taking a risk because I know my use case. 8,000 may not going to satisfy all the requirement, but again, like Saujanya has mentioned, like if you know your use case, if you know your data set, then absolutely you can go with this kind of a tokenizer.
Yeah, most of the optimizations are all about the economics of GPU, right?
Exactly. So GPU is the most expensive thing, and we are going to see about KV cache in 30 or in next 1 hour. Those are the places where you need to do all the optimization. Okay, so if this is clear, so you have two options. Okay, one thing I forget to tell you that obviously we need to start with installing some of the dependencies. Next, I showed you two ways. Either you can you can use the GPT-2 tokenizer, or you can utilize this script, which is the part of this GitHub repo. And what it is going to do, it's going to create the four file. One is human readable file, one which you can use in the script, and it's going to create train.bin and validation.bin. That's it. Then next part which came out, and here I'm just printing this, like what is the vocab size, and just one sample I'm taking. That's it. Next part is something called model configuration. So let's look at that. And this is going to be the long class, so I'm going to give you 5 minutes break after this so that you can stretch your legs and you can come back fresh. So the next part is the model configuration. Rajendra?
Sorry, sir.
So this part, we are not going to do any kind of a training, or we are not creating anything. We are just specifying, you can think of it like a blueprint. We are defining for our model. And these are the parameters we are going to utilize as a part of our training. So first thing, for example, we have just seen that we have created a vocab size, right? So I'm just defining it in the form of a variable over here, that this is my vocab size. Second thing is something called context length. So again, if you look at the Google Gamma and all these models, they now have the context length of like 100K, 1 million, 1.5 million. Again, my main idea is that I want to run it on a low-end GPU. So those are like, that's why I specify the context length as 2048. You can play with these parameters. These are all hyper parameter. So context length is, in the simple word, is like how many tokens your model is going to see before generating the next token. So let's say if I set the context size as a 4, these are the 4 tokens that model is going to see before it's going to generate the next token, which is the DA. So it's all depend upon your requirement. You can set it this as a high value, but just remember that during the inference stage or during the training stage itself, you need a higher GPU in order to perform that. Next is called embed dimension, which is the embedding dimension. So dimension, in the simplest of word, I always use this, is the characteristics. Okay, what do I mean by characteristics? So let's say, let's take simple example. Okay, not this or cricket. Let's say, just imagine that you have heard this word first time. You have no idea what cricket is. But if I'm going to give you some information, like cricket is one game, we use bat, like these are the famous player, like Sachin is one of the famous player. If I give you all these information, you will have developed some kind of a visual image, or you will develop some intuition about that word itself, the cricket, right? So all those different characteristics that I'm talking about the cricket, those are called dimension. So as a human being, Like if I'm giving you some more information about that person or that thing, you develop the intuition, right? Same thing happen with the model also. The more the characteristic you are going to define, the more the dimension that you are going to define, the more the model will understand about your data. So here I am starting with 384. Again, all these are a kind of a optimization thing. You can set the higher dimension also, like 3000, 4000, but again, you need a higher GPU. And we are going to do all these calculation when I'm keep on talking about the higher GPU required. So dimension, simple word, if you can think of it, is characteristic. The more the characteristic, the more you know about the data. Same way the model is going to know about the data itself. The next thing is called number of head. This is one of the functionality provided by the uh, uh, something called multi-head attention. So let me take a simple example, and I always use this example. The bank, and we are going to look at this into depth when we are going to see the GQA step. Okay. This is a complex example, and I always use this example for the purpose of demo. The bank near the river is closed. Here, the bank may have a different meaning for different people. Bank may mean financial institution, and bank can mean the river bank, the area near the river, right? So the main idea of the attention mechanism is when I'm talking about the bank, that means the financial institution. It need to pay attention to that particular thing. But people can have a different perspective. One people can think of it as a financial institution. One people can think of it in terms of river bank. So the earlier attention mechanism which was developed just capture one perspective. But if we want to capture a different perspective, like one for river bank and one for financial institution, we need to create the multiple heads. And that is the whole idea about this number of head. Like here in this case, we are defining 8 heads. That all these heads, they are going to capture different perspective from my data. Similar to that, there's some a concept called n layer, which is a number of layers. Any one of you guys remember about what the layer is all about? It is, just to give you a hint, it is something to do with same thing to capture different perspective. Any idea about layers? Yes, no.
So these are all the neural network layers that we are going to have, right? And each layer is going to have all those heads for the attention.
Yep. Something similar to that. So in order to understand layer, we need to go back to the attention is all you need paper. And I think all of you guys understand this. This is the paper which is responsible for the T part of the GPT, the transformer part. This paper introduced the idea of the transformer. And that is the reason we all are here, right? So if you look at this architecture, we have two parts. One is called the encoder block, which is not used anymore. And second one is called the decoder block. So when we are going to talk about the layers, that means, like, for example, in this case, they have used 6 layers. So that means this is one complete decoder block. So one decoder block, second decoder block, third decoder block, up to the 6th decoder block. So here I told you that we have the multiple heads, and the multiple head is used to capture different perspective. Same thing is they means researcher have seen that if you have a different layer, like different decoder block on the top of it, I've showed you guys this earlier. So like we can take this image. Where is that? Yeah. So think of it like this is one decoder block, and one decoder block means this whole decoder thing. So one, and the output of this will become the input for this decoder block. The output of this decoder block will become the input for this decoder block. And again, the main idea is to capture different perspective. Let's take a simple example. Let's say you are training your model for Python dataset. So one decoder block may capture that, okay, for Python, we need some indentation, like 4 spaces before I'm going to start the new block. There's one decoder block may going to capture like, okay, for this is a construct for loop, this is a construct for while loop and all those things. So different decoder block is going to capture different perspective in terms of Python. So what these guys have figured it out that if we have the multiple decoder block, we are going to capture the different perspective for our model. Let me ask, I think I've asked this question earlier. Decoder layer.
So each step is a layer.
Yeah, it's a layer. Layer means the whole decoder block.
Yeah, each one decoder block is a layer. And also, you said the encoder is no longer used. So what is it?
Okay. So sorry, before that, see, GPT-3 has used 96 decoder layers. So that means one decoder architecture, second, third, all the way up to the 96. GPT-4 is not publicly disclosed, GPT-5 no pub. So in this paper itself, they have used 6 decoder block. And if you remember that, this is used just for translation, for English to French translation. So, okay, just to quickly give you the idea about this. And LM3. So if you look at this diagram, you see till 2021, the model we used to create is called encoder, and I'm going to talk about that. From up to 2023, there is something called encoder decoder. And once the GPT-3 was released, entire world is now moved to the decoder based model, right? You can see any model, you can name it like Bard, which was the earlier name for the Gemini, Llama, this Claude, everything is a decoder based model. So if you look at this paper itself, they use the encoder part and the decoder part. And the reason for the encoder part, and let me tell you, this paper was used to do English to French translation. That was the main aim of this attention is all you need paper. So what encoder part used to do is to read these English sentence, and decoder part is used to do is to translate into this French sentence as simple as possible. But what these researchers, they have figured it out that when they have trained it with a massive amount of a data, and that is the first time these researchers, they were doing it on that much amount of a big text, they believe that this encoder part was not required anymore. They started seeing something called emergent behavior. What this emergent behavior means to do, that I briefly touch base on this, that the main idea of these LLM is to generate the next text. So we provide the input, like you're asking your question, that goes to the LLM and it generates one word, right? What you are seeing on your chat GPT or any of the LLM provider screen is a kind of a streaming output. But under the hood, it just generates one token. And when I say one token, so if DA is the input, the bank will be the output. If DA bank is the input, the bank near is the output. If DA bank near is the input, the DA is the output. Again, so on and so forth. So what these guys have found it out that when they have trained it with this much amount of massive amount of a data set, this encoder part is not required anymore. Like this model is capable of reading the data with this much vast amount of a data. Okay, let me take one step back. The main idea when they have trained this model is to generate the next token. That's it. But when they started training it with the vast amount of a data, sorry. So this is just for translation. Then there's a paper which came out, which is called GPT-2 paper. And most of the folks, they are not aware of this paper because this came back in 2020, which is like way before, like 2022 is the one when the chat GPT was released. So this paper came out in 2020, and this was course completely unnoticed. But the main idea behind that is that when they started with this massive amount of training data, the encoder part, which is required to train to read the data set, is not required anymore. So simple example I can give you. to French, right? And I can pick any sentence. Like, let's say I pick this one. And you know that nowadays, all the LMs, they are capable of converting this, like, is able to perform these tasks. So we don't have the encoder, right? Encoder work is just to encode or to read the text. But because they have trained it with this much massive amount of a data, that encoder part is completely been eliminated. And what I feel that GPT was the first model which was released, and they followed this architecture. And in this paper itself, they have not talked about like whether they have started with the encoder and then they switched to just decoder based model. They said that they started with the decoder itself. And they said that decoder model is capable of reading as well as translating the text. So that is why the reason that encoder based architecture is not used anymore. Most of the provider, they switch to this decoder based architecture, which you can see in this image itself. Is this part is clear or?
Yes.
Okay. So there are a bunch of other parameters. I think this is going to create more confusion if I'm just going to talk about all these parameters. I just talked about few of these parameters, but I think much better when we are going to utilize in our code. I'm going to refer it back and then show you what part of the code this parameters is being utilized. So I know we are in this call from last 1 hour. Let's take 5 minutes break because this is going to be the long class, like I told you guys. So just take 5 minutes break and we will meet. Okay, Krishna, you have a question?
So much of these numbers that you used here while
Mhm.
setting up the model,
Yeah.
did you actually customize each and every stuff, or did you use anything by default?
No. So to be honest with you, the default parameters, those are pretty big, which is used by this gamma paper itself.
Okay.
These were. So I have the experience of building these models. So whatever the parameter that I've utilized over there, I just copy some of those. So there's no hard and fast rule. These are all hyperparameter. Please feel free to play with that. But the main idea is like, for example, if you are not going to do this kind of optimization, let's say this here where we are creating train.bin or validation.bin and saving it to the disk. If you try to do it with a GPT-2 tokenizer, and if you try to run this model on T4 GPU, you will run into out of memory error.
Okay.
So again, like I told you, if you have a sufficient amount of a GPU available, you don't even need to worry about all these things. But we all know we are all are GPU poor, right? So these optimization just done to prevent those kind of errors.
And these parameters, I mean, we can use in multiple use cases, right? Without tweaking their value. So my only point is that, I mean, getting these parameters and going in depth, okay, we should know that, okay, what each parameter is doing. But
Yes.
again and again, tweaking it and playing it with will changes the result. I mean, it will make different models more realistic.
Yes. So for example, context length of 2048, no one is using that lower of a context length. The minimum context length that I have seen is 4096. But again, my main idea is not to play with that thing. The main idea is to run on the minimum amount of a GPU. On the top of that, for example, this head dim and global dim, these are something specific to Gamma. And there are other providers who is using this kind of a setting, which I'm going to talk about, something called sliding attention. So these things you need to pay attention to it. But otherwise, all the code that I'm going to show you, that is going to apply even for Llama, not totally to the DeepSeek, because DeepSeek uses something called multi-level, multi-latent attention. But most of the model provider, even I have checked it for the NVIDIA Nemotron, the same code exactly going to work on all of these models.
The only benefit is that we can use this script and all these stuffs just to have the model ready on our own local
Yes.
laptop.
Local laptop, GPU, anywhere you will be able to do it. Again, I think I've shown you guys, most of the cases, you don't even need to worry about all these things. So you are going to use some kind of a framework. Like this is one framework, there's something called Megatron. So most of the time you're going to use these kind of a framework, and you just not need to define the parameters. So for example, there's a parameter for tokenizer, and you're just going to specify that you are going to use GPT-2 or GPT-4o. And under the hood, whatever the code we have written, it's already been written over there. So these are kind of a frameworks which is already been defined. Whatever we are discussing it today or tomorrow, these are all under the hood stuff. And these are the type of a question which is mainly asked during the interview. Or if you are applying for the companies like Anthropic or OpenAI, these are the type of a question which is been asked, like OpenAI, Anthropic, and even I have interviewed in Meta. Those guys ask these kind of a question. Honest with you, 90% of the world, they have no idea about all these things. Uh, After this, you go into the 10% people who have idea about all these parameters, and at least have, I am not going to expect like this, I'm building it from the last 2 years and now I have some amount of a confidence, but at least I want you guys to have a high level overview of all these concepts.
Yeah, making sense.
Okay, so guys, let's take 5 minutes break and let's be back on 9:13 sharply. Is everyone is back? Shall we start?
Yes.
Okay. So we stopped at a point where we discussed about the gamma configuration. Let's look at the next part of the code block. Okay, I think rope, I think it's much better when I'm going to talk about the model configuration. Sorry, the model. So let's skip this part. We are going to revisit that. Let's look at the next part, which is called RMS norm, which is called root mean squared normalization. And if you are going to look at this architecture, this is what I have built. But if you look at the one of the blogs from the Google itself, not by the Google, this guy works for Google. You see that RMS norm is utilized at many places. Here, 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 here. But before we are going to discuss about that, any one of you know what is the use of normalization and what is the problem it solved? Any idea about it?
You're going to flatten the values
Yes, but why?
because you don't want too big of a value or too small of a value, because you want to represent I mean, depends on the model like that you're using for classification or uh,
To bring all under same unit.
Yes.
I mean, to make the model more consistent.
Not exactly consistent, but the main idea behind that is to introduce something called training stability. So if we take this image, okay, the main idea behind the normalization is to prevent a problem called vanishing gradient or exploding gradient. So I can give you the simple example again. Like, let's say I trained the model with a bunch of images of cat and dogs, right? And this is the input layer. Here, these are called weights and biases. These are called learned parameter, what the model is going to learn. So when we are going to pass the images of a cat and a dog, it will go through these layers. Remember that the first time when we are going to start, or this is called the forward propagation, all these weights and biases, they are going to initialize randomly. And as we are going to train it with a large amount of our data, all these weights and bias, they are going to be updated so that it is going to learn. And in future, if we are going to pass it a new image, it will be able to predict the cat and a dog. But what exactly is going to happen? Like I told you that these are all the weights and bias, they are going to be initialized randomly. And let's say I pass the image of a cat once the model is being trained, and let's say predict dog. So what it is going to happen, there is something called back propagation. So this is called forward propagation. The reverse path is called back propagation. And in case of a back propagation, what it is going to happen, there is something called optimizer, which is Adam W. We are going to use it. It's going to update these weight smaller by smaller bits at each and every layer, so that the next time we are going to ask that question, it is going to give us a good prediction or the correct prediction. Now the problem is, like in case of a deep neural network, and deep neural network means all these LLMs, which are the deep neural network. Like I'm showing you these small, some of the number of hidden layers. LLMs like GPT, they have hundreds and hundreds of these hidden layers. So the problem that happened that by the time this backpropagation going to happen and these weights are getting updated at each and every layer, by the time it reaches to the all these inner layer, these weights are become so small that these weights are not getting updated at all. So these layers are not getting updated. That means your model is not getting trained. And that is a problem. We called it a vanishing gradient problem. And in some of the cases, these weights become so big, your model is not getting updated. So like what Krishna has mentioned, that we need to keep these weight under the optimum range. And one of the solution which we implement for that purpose called normalization. We need to normalize these weights so that, just understanding in simple terms, that in order to have a stable training, you don't want these value to become too big or too small. We need a optimum value, and normalization help in that case. So in order to perform normalization, What these guys have done, they use a formula for something called RMS normalization, which is called root mean square. And with these guys means the guys from Google. Uh, so they are using this formula. Here, if you can see, they are calculating the mean like xi. So they, if you have a value like 1.0, 2.0, 0.1, all those, they are taking the mean. They are adding it with epsilon value. So epsilon is just a small parameter they have introduced just to make sure that there will be no divisible by zero error. So that we don't want to make those value to become infinite. And then we are dividing that value. And there's one more parameter they introduced called scale parameter. So what we are doing it over here. So if you remember that before this, most of the provider, they use something called layer normalization. Layer normalization formula. This was a formula for layer normalization where they do bunch of these things, like they subtract the value of their input value with the mean, then divided something called variance, they added epsilon. What the guys from Google, they have figured it out that we don't need to subtract it with the variance. They are getting a much more training stability if they are just dividing it with something called mean itself. So here, if you see, like, okay, I think it's much better if I can show you with the help of an example. So let's say if this is a formula. So what we are doing it here, let's say my input value is x is equal to 0.1. I'm taking any value 0.2, 0.3. So first thing which we need to do is to calculate the mean, and mean is nothing 0.1 plus 0.2 plus 0.3 divided by the number of values. So here we have the three value 1, 2, 3, right? So that will be the mean. So what we are going to do, we are going to, like, the first iteration will be 0.1. We are going to put this value over here 0.1, divided it with the mean, which will be the value of this 0.6 divided by 3, which is going to be 0.2. So this will become 0.1 divided by 0.2. Epsilon will be a very small value, which is going to prevent it for divisible by 0. And then we are adding another value, which is called scale factor. Anyone has any idea about the scale factor?
Yeah, zero dimension tensor.
Zero dimension tensor, but what is the use of that?
For scaling, we can increase.
Okay. So the main idea behind that, the scale factor is a kind of, again, a hyperparameter. And whenever we are talking about the hyperparameters, that means these are, sorry, not hyperparameters, these are called learned parameters. So simplest way to understand this, that, okay, I have done all these things to normalize these weights of our model. But let's say even after the normalization, for some of the weights, we see that there is still a problem of vanishing gradient. So what we are saying, that we are giving a free hand to our model, that for all those weights, you can add some kind of a hyperparameter just to prevent this vanishing gradient problem, so that it will not become too small. So for most of the cases, it is absolutely right. Like once we are going to create the mean, that thing will work. That this will not going to happen, the vanishing gradient problem. But all those edge cases where even after implementing these formula, there are some weights which becoming still so small. So we are just giving the model free hand that either try to increase or decrease those value just to make sure that it will introduce some kind of a training stability. So that is why the idea of the scale comes in. So simple thing we are doing, this is just to introduce a training stability, just to make sure that the weights which is being propagated across the layer will not become too small or too big, that will introduce some kind of a training stability. And one more thing which we are going to look at in next step, that there is something called a softmax, which is going to prioritize the value which are high in number. So if there is a value which is like 0.1 and there's a value called 8, it is going to prioritize these values. So that's why, for that purpose also, we don't want one value to dominate our entire data set. So that's why we introduced this normalization. I think this is the most simple thing which we have talked so far, that the main idea behind that is this line, where we just converted that line, the code that we have seen, into the formula. This thing.
Can we consider normalization is one of the activation function? This RMS norm is one of the activation function.
Activation function, no. Activation, those are the different function.
Those are different ones.
Activation, we are going to see it in the step number 6, which is GELU.
Okay.
GELU. So this code is pretty simple. What we are doing it over here, like x dot torch, there is a function called square root. But when you do r square root, that means 1 divided by r square root. So what we are doing, x to the power of 2 mean minus 1. This is the same thing which is present in this formula itself. Then we are adding with the epsilon, and then we are adding it to the scale factor, but we are not adding scale factor for all the condition, just for the condition where it's becoming a so small that we need to add those scale factor to it. That's it.
Okay. And one doubt, how we are reaching to that vectors from our token ID to vectors?
Token ID to vector, this is what we are supplying it over here. This is what coming from the top itself, the
No, no.
data or the input.
You take an example, right? You took a small text, right? So for vocabulary size, each token will have a token ID, and each token IDs will be converted to the vector, right? Like
Okay. I got it. What do you mean by that? So this is the layer where we are going to specify this RMS norm. So what we are going to do, we are going to take the token ID. Let's say this is a token ID. Okay, let me take one step back and explain to you this flow. So let's say this is a token ID, right? So now just remember that inside this whole of this block, now there is no meaning. Let's say this one, gamma. Inside this whole of your transformer block or whole of your this pipeline, there is no meaning of gamma. The way it is going to understand with this number of called 300. Now, what it is going to do is that we are going to initialize this embedding layer. And how we are going to initialize this embedding layer? Again, randomly. Let's say these values are 0.2, again 0.5, 0.6. And I'm taking 3 dimension just for the sake of simplicity. What it is going to happen, again, for this layer also, the lot of training is going to happen. These weights are going to be updated, and these weights are going to be have the value at the end of the training. That at the end of the training, it's going to understand that 300 stand for gamma. And how it's going to understand it? With these value or these weights going to be updated. That is the thing which is going to pass to your RMS norm block. That the meaning of gamma or the word itself is there. This is again oversimplified explanation. Most of the time we don't send a single word. We are going to send the data in the form of a blocks that we are going to see in next few minutes.
Yeah.
So this is the RMS norm. Then the important part, which is called grouped query attention. I think some of you guys must be aware of this grouped query attention, right? Or GQA. So let me start with the attention mechanism, and then we are going to discuss about all these this group query attention. So main idea behind the attention mechanism is that how much attention we need to pay to the each and every part of the sentence. So if you look at this word, or I can take a simple word, the cat sat on the mat. And if I'm going to ask you who is sitting on the mat, then you can say this is a cat, right? Trust me, before the introduction of this transformer architecture or before the introduction of this attention, it is pretty difficult for the neural network earlier to look at this kind of a like to figure it out which part of the sentence we need to pay attention to. And again, I'm telling you that this attention is all you need paper. Where it is that? Is the word is a kind of a misleading, because attention mechanism by itself is figured out in this paper by Bandana way back in 2014. These guys introduced the idea of T transformer. So the main difference between this paper and this paper is that this paper, which came out in 2014, introduced the idea of attention, like how much attention we need to pay to the each word in the sentence. What the idea introduced by transformer paper is that how to feed this data in parallel. Earlier neural network, if I need to train the model, each of these word or token, I need to feed it sequentially. But what transformers can introduce is introduce that all these tokens I can feed in the form of a batches of data in parallel. Now, attention, simplest word is that how much attention we need to pay to the each word. And in order to do that, they come up with this formula, which is called this one. Right? This is the way we calculate this attention score, or we calculate something called a context-rich matrix, where each word know what is its neighboring word. There they introduce a formula called, they introduce the idea called query, key, and value. Right? Query means what exactly we are asking. Key means what exactly we are offering. And value is the final value or the desired result. So again, let me take this simple example. I always use this example because it's easier to demo it. Let me see this. Yes. So here in this case, if I'm asking like, what is the name of the employee ID number 27? So the question that I'm asking is the query. Like, what is the name of the employee 27? Key is what exactly it can offer. Like here it is key is 10, 27, 33. And the value, like if I'm asking about the employee ID 27, the value is Michael. So this is the whole idea of query, key, and value, like what we are asking, what it is offering, and what is the final output. And this they have did it in this, they have formulated in the form of this whole, this formula. So the main idea is how to calculate the attention between the different word in a sentence. Now, this is the first formula which came out, which is called self-attention. Okay. Now, then after that, the attention mechanism which came out is called causal attention. The main idea behind causal attention, like I just told you a few minutes back, that what LM is doing, it's just generating one token at a time. Okay. And what we have done as a part of this attention mechanism, that we have exposed all these tokens, which is a kind of a cheating we are doing to the LLM. Like, for example, if you look at this sentence, your journey start with one step. Here we are exposing all these words. But under the hood, like when we are going to do the inference, what LLM is going to do, if your is the input, journey is the output. If your journey is the input, start will be the output. Your journey start is the input, with will be the output. So what we want to do, we need to do the masking of all the future token. And that is the idea of causal masking. Like if your is the input, your journey will be the output. So it will only be able to see these two words, not any of these future token. So if you see from the diagonal itself, we created the masking. But the main idea is that start can see all the previous token. Like start can see journey, your, with can see start, journey, your, but it should not be able to see any of these future token. That is the whole idea about the causal masking. Now, after this causal masking, they come up with something called a multi-head attention. So again, the same example that I gave it to you guys, the bank near the river is closed. The earlier attention mechanism was called self-attention, which can capture only one perspective. So it can only capture either this will be a river bank or this can be a financial institution. It cannot capture both the perspective. So in order to do that, we create something called a multi-head attention, which can capture the different perspective. Like one head is going to capture that this is a river bank. One head is going to capture that is a financial institution. Okay. Google has done all the other optimization on the top of it, which we are going to see. But after doing all these things, like we started with self-attention, where we only have one perspective. Then we find out the causal attention, where we are trying to hide all the future token. Then we come up with something called multi-head attention, which is the main idea to capture different perspective. Now, this is all we are doing at the part of our training pipeline. Let me shift back to one more thing, which is called a KV cache. Okay. So the main idea behind the KV cache, that this query which user is asking, and again, this is for the inference part. Now we are shifting gears and we are on the inference side where the model is trained and we are asking question to the model. So here, what these guys have figured it out, that this question which user is asking, it's keep on changing. Like one time he's going to ask about the employee ID 10, sometimes by employee ID 27, sometimes about 33. So this query is keep on changing. But these keys and value, let's say these are like a 10 million rows, these are always static. So rather than recalculating all these things, why can't we do cache these key and value? And that thing is called key value cache. Okay. So the idea is to cache these keys and values so that we don't need to do the computation again and again. But that lead to one drawback, which is called, let me show you. KV cache. One second, guys. It should be the formula for KV cache, yes. But this KV cache has one limitation or one drawback, that in this case, let's say if I'm going to take the example of Llama 7B model, okay, this is the formula it is required to calculate the KV cache. And remember that KV cache is per session. So if I'm interacting with ChatGPT right now, that is one session. If you guys are interacting with ChatGPT, that is one more session. So this KV cache is going to build per session per user. Okay. So here, if you can see the L stand for layers. That is, I told you that there is a stack of transformer block on the top of each other. Where is that? I showed it to you guys earlier. That this is one decoder block. And for example, in this paper, they have like 6 decoder block on the top of each other. So that L part here is the layer. B stand for block size or context window. Again, the amount of token the model is going to see before going to generate the next token. S is something called a sequence length. Oh, sorry. This S is sequence length, which stands for context window. B stands for something called batch size. So like I told you, we are not going to send a single token. We are going to send a bunch of token in terms of batches to the model. And again, because transformer is capable of handling those token in parallel. So that is stand for something called batch size. Context window is the amount of token the model can handle at once. Then we have NKV. This is the most important parameter, and it is going to determine that how many number of head we have split it into. So for example, in our use case, like for example, in this case, let's say we split into 2 heads. One head, it is going to capture whether it's a financial institution. The other head is going to capture whether it's a river bank or not. So that we are going to make it 2. Then there is a parameter called H. H stands for dimensions. Okay. So we have seen the dimension, like the number of characteristics. We need to define it like this. Then we have 2. The reason we have 2, because 2 means we are capturing it for key and value. So that is why this 2 number is coming in. Then there's something called bytes per element. This bytes per element is going to define like what is the data type we are using to train our model. Let's say if it's a 32-bit, then we all know that 1 byte equal to 8-bit. Then in that case, this is going to be 4. So 32 divided by 8 is equal to 4. Same if this is 16-bit, then it is going to be 16 divided by 8, then it's going to be 2. So if we are going to feed all these value for Llama 7B model, it came out to be 2 GB. So this is per session. So each user is need 2 GB of memory again during the inference stage just to store all these KB cache. And that is going to be pretty expensive. So what the researcher had determined that this solution is not going to scale out. Let's say if I need to serve 100 user, then in that case I need 200 GB of GPU memory just to serve the KB cache. So in order to solve this problem, they come up with something called MQA, which is called multi-query attention. And multi-query attention is the same idea. Let me show you with the help of an image. I think it will be much clear. So main idea about the multi-head attention that we have a different head, and each of these head, they are capturing different perspective. But what these guys have done in the case of multi-query attention, we have different head. But let's say this is a key matrix. What they have done, like this is like first key matrix, this is second key matrix, this is third key matrix, this is fourth key matrix. They just copied these key, this first one key to here, this first one key to here, the first one keys to here. Same thing they have done it for value matrix, that this value matrix, they have copied this value from here, they copy the same value here, they copied the same value here. So now all the head, they have the identical key matrix and the value matrix. And the advantage of that is, for example, this parameter NKV. So let's say in this case, this value is 4. For multi-head attention, this value now become reduced from 4 to 1. Because all these key and value, and remember that this is a part of the inference, not training. So when all these heads, they have the same key and they all have the same value, this value of 4 will be now reduced to 1. So earlier it was taking like a 4 GB, 2 GB of memory. Now we can divide it by 4. That means 500 MB of memory per session. But the disadvantage of that the main idea we come up with this multi-head attention, that all the heads, they need to capture different perspective. But when we copied all the same data to these key and value to all the heads, that perspective is completely lost. And just to tell you, this MQA is not used anymore because of all these limitations. Then they further optimize it, and then they come up with the idea of something called GQA, which is called group query attention, which is a kind of a middle ground. Here they are saying that, okay, if we are copying these keys, same thing, you can think of it for value also, then we are completely losing the perspective. But what will be the case? We can create groups. So rather than having the same keys copied to all these, let's create one group. Like let's say this is one group. This will be the second group. And now these two groups share the same key. These two groups share the same key. So it is not as good as multi-head attention, but it is somewhat at the middle path where these two will sharing the same keys. These two will be sharing the same keys. So earlier it was like 4 head. Now we reduce with the help of group to 2. So if it's taking 2 GB of memory earlier, now we reduced it to 2 divided by 2, which is equal to 1. So we started with 2 GB per session. We reduced it to 1 GB. Now we reduced it to 500 MB. So this is not a perfect solution, but it is a kind of a middle ground between MHA, multi-head attention. Then we have this group query attention, which is a kind of a middle ground. And in the end, we have the MQA, which is not used anymore. Again, this is for the inference side. This is not the part of our training. But in order to explain to you the GQA, I need to introduce this KV cache. And the main idea is how we are utilizing these key and value pairs. And why we are talking about all these key and value pairs? Because in order to calculate the attention score, this is the formula they have given it to us, guys. And where we have this key and value and query key and value. Is this part is clear to everyone before I'm going to show you guys some of the other optimization which is introduced by Google? Any question related to the group query attention or any attention mechanism which we have discussed so far?
So Prashant, when you were saying you were grouping the keys, right? Or cloning the keys, copying the
Cloning the
keys.
keys,
Okay,
cloning
why
or
is it
copying the
called
keys.
a grouped query instead of grouped key?
So query always remain the same. Query, we are not changing anything. It's just the keys and value that we are grouping. We are grouping all these keys and these keys. So there is one query which has been split across these multiple keys and values. So main idea behind that is, I know it's a kind of a misleading, but the main idea is grouping these keys and grouping these keys. Same thing for a value also. Query, we are not touching.
Okay.
In the above example, right, the employee name and ID,
Mhm.
can you relate which will be the keys and which will be the values?
So key, these are all the keys, these are
Okay.
all the values. So if
Okay.
this is one head, then this 10 will be copied to other head also, or the other key matrix also. If this is 27, this will be copied to other one. So both the head, they are going to see the same keys. Whereas these values, same thing. If this is Sarah on one of the value matrix, the other value also have the Sarah. So that is the reason that it will lose those perspective, but it is not going to be bad as MQA. It is little bit of a middle ground between this MQA versus the MLA, which is the MHA, which is a perfect one. So again, not in terms of training, think of it in terms of inference, where we want to save our GPU memory. So here we are coming into the middle ground where we started with this 2 GB of memory. Here we reduced to 1 GB, and there we have reduced it to 500 MB. Okay. Now let me talk about two things which has been introduced by Google, and it is used by other models also. You may have heard about something called Mistral, and there's something called Olmo also, which is using these kind of optimization. So one is called Mistral. There's some other model called Olmo also, which is using group query attention with something called sliding attention. Any one of you heard about this sliding attention? Okay. So if we go back to this example, where is that? I have shown you that here, what we are doing it over here in a part of a causal attention or mask attention, that we want our model, or not our token, to not to see any of the future token. But like I told you, this, if we take the example of this one now can see what is there in the your journey start with. What Google or these guys have done, they even prevent the model to see further back in the past. So for example, this one can only see with or start. It will not be able to see your or journey. So let me show you. I think it's much better to visualize with the help of an image. So it's called sliding. Yes. So this is a regular attention mechanism, right? Where if this is a word, the cat sat on the. So you see the on is capable of seeing the cat sat, right? But it is not capable of seeing all the future token. What these guys have done, they have done something called sliding window attention. What sliding window can do, you see if this word is the is only capable of seeing on. It can't even see all the past word also. That it cannot see the cat sat. Same thing is with on. On can only see the, but it cannot see all the past token also. And what these guys have saw, like if you're going to read this paper, that they have seen a lot of improvement in terms of memory utilization, and they're able to extend the context window also. But you can think of it like in regular attention, again, the main idea behind that to capture different perspective from your data. But here, if you can see it over here, we are losing that perspective. DA is not able to see all the past token. So it may not able to capture all the data from your token or from your data set. So what Google has done after that, that they introduced something called a mixed kind of a window. So this is first thing is called sliding window, the sliding window, and they introduced something called global versus local attention. That is the naming scheme they have used. Global means the old attention mechanism that we have seen earlier, that where the token can see all the past token also. But then they have the local attention. So what they have done is they have split it into 5:1. So first 4 layers will be the local attention where it cannot see all the past token, but there will always be one layer which can see all the past token also. So that's why they're calling it like a 5:1, where they have the 5 layer. 4 is all local attention, but the 5th layer is always the global attention. Same thing over here also. Like if you have the 35 layers, the first 4 layer will always be the local attention, but the last layer will always be the global attention. So they believe it's a kind of a more of a memory efficient kind of a thing, where there are some layers which are only calling locally, whereas there are some layer which are calling globally. And if you look at our configuration also, there is other thing which they have defined, like for example, for local attention, they define the dimension as 48, but for global uh, uh, heads, they are defining the dimension 96. And again, the reason behind that, because global head is capturing more perspective. So they need more dimension. Whereas the local head, they are not capturing all the perspectives. That's why they defined a lower dimension for that. So that is one thing which is introduced by Google, and other model provider. They're also using this sliding attention, where it cannot see all the token in the past, but there is always one layer which is capable of seeing all the token in the past. So it's a combination of like 5:1, 4 local layer, 1 global layer, then 4 local layer, 1 global layer. So if you have a 20 layers, let's say you define, 4 will always be local, then 1 will be global. And if this is 5, then you will know that this is going to repeat 4 times, right? It's always been 4 local layer, 1 global, 4 local, 1 global, and so on and so forth. So this is one optimization which is done by Google or with other model provider. There is also called KV layer sharing. Okay, but I just told you that these will already been shared, right? For example, in this case, these keys are already being shared between these head, right? This is between these head. But the optimization they have done at the layering level. Layer, again, just to remind you guys, layer means one decoder block. So what they have seen, like let's say if this is an example of 20 layers, what these guys have seen that, okay, we have all these different layers, because these different layers, they are capturing different perspective. But some of these layers, they can share the layer with themselves. So for example, if this is layer 1, and let's say all the way up to layer 20, right? So what these guys have seen, that all these layers, they don't need to have this dedicated KV cache. Some of these layers can share the KV cache. So for example, this layer 20, I'm just throwing an example. This layer can share the KV cache with this layer. So if you look back our code, there is something called, where is that? There is a parameter, this one. So in our use case, we have 20 layers. And again, I told you like 4 local, 1 global. So out of those 6 layers, we can choose it as a shared layer. So 14, they have a dedicated KV cache, but for 6 layers, we can have the shared cache, that they can share the cache with the other layers also. Because these guys have feel that not every layer, they need its own dedicated KV cache. Is this point is clear? Because these are some of the parameters which are specific to the Google Gamma. Whatever we have read it so far, like GQ and everything, those can be applied to any model. But these things like KV layer sharing, let me see. Except Google Gamma model. Does any other model use this? Because I am not aware of any other model which is using this concept of KV layer sharing. So KV shared KV layer, very common use. Oh, so they're talking about shared KV, which is different thing. Yeah, rare and interesting. Gamma is the only one who's using this concept. So just remember that this is something specific to gamma. Other concept that we have read that can apply to any models. Is this point is clear to you guys? Any doubts so far? Any question? Okay.
All other models are using casual attention.
So that's what I told you. This is different idea, sharing of this layer. This idea is different, sliding attention.
Okay.
So yes, other model, they are using the causal attention, but Mr. and Olmo, okay, let's ask ChatGPT itself. Using sliding window attention. So one is Mistral, who is using it. Mixtral, I have never used it. Gamma for sure. Long former, no. So yeah, out of all these, I think this is the popular one, which is the Mistral, which is one of the European-based company who is using this sliding window attention. So you can think of it like Mistral and Gamma, they are using the sliding window attention. Rest of the models, they are using, yes, the causal attention or the global attention. So you're right.
So Prashant, I just want to see the part because you are specifying all the things which are required for gamma model, right? All the
Mhm.
values and all the parameters that it requires. But where did you actually import? Is there a library that it's in
No,
the
no,
code?
no, no, no. So we are going to call all these parameters when we are going to build the model.
Okay.
So there is no library or something like that. We just define it and you will see. I show you. So when we are going to build this model, we are just going to call this out. There is no library or nothing like that. That's what we are building it from scratch. We are not using any of the framework to build these things.
Right.
So there is no such library or nothing like that.
So it's just some specifications, and ultimately what you're going to do is, what is going to be generated is a gamma model.
Yes. So this model is available on Hugging Face itself if you want to play with it. Where is that? And I mean, you have the notebook. Please feel free to use that. So this model is present on Hugging Face. You can play with it. And on the top of that, the trained model itself, not this one. Where is that? This one. All the weights and biases, I've already published it, or the tokenizer also. I have also already pushed it to the Hugging Face. And I gave you the instruction how to use it. And even if you don't want to do that, I show you this demo where you can ask the question. But I want you guys, even if you don't have access to GPU, and I believe you guys must have Mac or some other operating system or some kind of a laptop, you can use this part of the code. It is going to take at least 7 hours to be trained, but then you can play with the model in your local laptop itself. Okay. So let's look at the attention code. And if you're going to look at this attention code at a first go, it looks scary that this is the code. But if you go down and if you can, like, what is the main part in this code is this part. This part. If you look at this part of the code, can you see any resemblance to any formula that we have looked at it? And it is the same thing which we are doing it over here. Can you see here? We are multiplying queries with key transpose. Then we are filling it with all the infinities so that the softmax of infinity will become 0. We are applying the softmax. And then we are multiplying these attention weight with the value matrix. Which formula is this?
Causal attention.
Exactly. So that's the only thing we are doing it over here. This one. We are multiplying query with key transpose. We are taking the softmax after that, and then we are multiplying with value. One thing which these guys are doing specifically, which is been mentioned in this paper, which those guys are not doing, is divided by dk with the dimension of k. So dimension of k, again, it's one of the normalization technique just to make sure that our weights will not become too big or too small. But in this case, if you are going to look at this formula, after defining these query, they are doing the normalization after that. The RMS norm that we have done, they are doing it for all the queries, keys and values. Sorry, only queries and keys they are doing it. So we don't need to divide it with dk. Except for that, this is the entire formula that we have defined it over there. One more thing, if you look at this entire code, here we are just checking if the layer is sliding or not. So for example, like I told you, the 4 layer will be the local one, and then we have the global one. So we are just checking which layer is the global one and which layer is the local one. Next, we are checking the KV share that I have told you, that whether we are sharing the keys or not, or layers or not. So if you look at above, again, if you go back to the code, I told you that out of the 20 layers, only 6 of them, they are going to be the share. So that's the only thing we are defining. The main key takeaway from this formula itself is that we are calculating the attention score over here. And attention score is just nothing but how, or the context factor, that is nothing but how much attention we need to pay to the each and every word of the sentence. That's it. So if you understand that part and understand what are the some of the innovation which is done by the Google, which is this global versus local attention and this KV layer, cache layer sharing, that's the only thing we are doing in that formula. That's it.
Sorry, can you explain why we are not dividing by dk?
So why we are not dividing by dk? Because these guys, what these guys have done that, okay, so let me go back to here. So where is that? If you look at here, right, the embedding, that is what we are going to pass to the RMS norm, and that is going to pass to our transformer. And if you look at this small part, we are doing something called QK norm, which is called query key normalization. Okay, they have not explained why they have not done it for a value, but most of the time they've done it for QK norm, right? So the main idea behind that if you are going to read this paper, the reason they divided with underscore dk is that if you see it over here, we suspect that for the large values of the dk, the dot product grow large in magnitude, pushing the softmax function into a region where it is an extremely small gradient. So again, I think I've showed this code earlier also. And this is what we have. So there is one issue, I will say, with a softmax function, that if the values become high. So for example, if you look at here, this is 0.5, 0.15, 0.4, 0.1, 0.25. If we are going to take the softmax of this, what the softmax is going to do is how much attention we need to pay to the each word. So here, if this is some sentence like the cat sat on the, what we can say that we are paying 18% attention to this word the, we are paying 15% attention to cat, we are paying 26% attention to sat, on 16% and 22%. But if we are going to multiply it with, let's say, with 6 here in this case, these value will become higher. And here in this case, you see that here it is completely changed. Here we are only saying 7% attention, 2%, and 61% attention to this word. So what softmax is going to do, it's going to make our training unstable, where it is going to pay so much attention to the one word and it's going to completely neglect all the other words, these word and these word. So in order to prevent this, what these guys have done, they divided with something called underscore dk, just to normalize these values. Again, the whole idea about what we are doing it here to make our training stable. But either we can do this normalization, or what these guys have done in this gamma paper, that they implemented something called QK norm. Rather than dividing it with dk, whatever the values which are coming here for query and key, they are just applying the normalization function here itself. Yeah, Sharul.
Uh, I read the notes on the lab for the gamma model. I guess in the notes at this, I read that they do not assume a separate notation for V, or they don't care about the values. They just assume that the keys are the values. So the K and V are the same tensors. And that's why you're seeing here QK norm instead of.
Not totally, because that's what I'm going to talk to you guys tomorrow. That in some of the cases, if you see it over here they have used K equal to V also. So they assume that for some of the layers, the value of key and value will be the same. But we are going to discuss that tomorrow. But here the whole idea is about QK norm, which is applying the normalization at this layer itself. So again, the main idea is to have the training stability, and we don't want one value to dominate our entire training. We want that all the weights which are present in our model, or all the data which are present in the model, have the equal attention, and everyone is contributed to the training itself.
Yeah, it seems like when you are doing the QK norm, and probably we don't get the higher values. It's all
Yes.
cosine and
Yeah.
So
Not cosine, not cosine.
not
QK norm, we have seen this formula. This is a formula.
yeah, we need
Not
not use that. Yeah.
okay.
And also applying the softmax is giving the probability distribution values.
So what it is going to happen, that when you are going to multiply this Q with KT, that is going to give you some kind of a attention score. So I can show you. Okay, let me take one step back. Okay, let's start from here. I told you that we started with tokenizer, right? Tokenizer, let's say this word cat has the token ID of 20. Okay, and I have told you that this 20 is now goes to the model. Model has no idea about cat now. The only way the model is going to recognize this word with this token ID that has been assigned, right? And then based on this token ID, we are going to create something called embedding matrix. And how this embedding matrix look like, for example, in our case, we have the vocab size of 8,000, right? So we are going to create this embedding matrix where we start with the position 0. Somewhere down the lane, we have this position 20, and it will end to 8,000. And then in our use case, we have defined the dimension of 512, right? So 512, it will be somewhere, it will start with some kind of a dimensions. For example, cat, we have one dimension for sound, let's say. So it has some value of like 0.2. Then it has tail, so it has a value of 5, all the way up to the embedding dimension, which will be the 512. So it will have all the 512 values, which we are going to initialize randomly. And these random value, we are going to do the training, and with the back propagation and everything, these value will get the final value, which will going to give us a good prediction. Now, these embedding metrics that we are going to pass to the RMS normalization, and then we are need to build out of these embedding metrics something called a context vector. And context vector is nothing but how each word can correlate to the other word in a sentence. Like the cat sat on the mat. Okay, so if I'm going to ask who is sitting on the mat, the cat, we are going to calculate the attention score. And that attention score is calculated based on this. But embedding matrix has no idea about its neighboring word. Like cat has no idea about that. The cat has no idea about sat. Cat has no idea about on, the, or mat. So right now, this embedding matrix we have has no idea about its neighboring token. So what these researcher has done, that they come up with the 3 new metrics, and that is the idea that has been used in research for a long time, that when the researcher, they are not able to figure it out how to solve this particular problem, what they have done, they come up with 3 new embedding, they come up with 3 new metrics, which is called query, key, and value, which we have discussed. Again, they are going to initialize this randomly, and they are going to assume that when we are going to train with the large amount of our data, these value will be updated. And what they have done, like this query and key, they are initialized randomly. What they have done, that when they multiply this query with key transpose, this one, they will come up with some kind of a attention score. And this is the score like how much each word is paying to another word. But these value will come like 0.2, 0.3, 0.5, let's say anything. So here I cannot say quantitatively like how much attention cat is paying to the, how much attention cat is paying to set, how much attention cat is paying to on, how much attention cat is paying to the, and so on and so forth. So that's why we are going to apply something called softmax. And what's the beauty of the softmax, that if you're going to add these values, this will become 1. So now after, let's say, applying softmax, this will come as 0.3, 0.5, and 0.2. So now we can, if you are going to sum up this, this will become 1. So we will say that cat is now paying 30% attention to the, cat is paying 50% attention to set, cat is paying 20% attention to all. So that is the advantage of softmax, that we can quantitatively say that after applying the softmax, it will become 1, and model can able to see that how much attention it is paying to different words. This is just for only for that purpose.
Okay, so instead of this,
Yeah,
one
that's
way,
what they say weight, right? So it's giving weightage to the each word.
Exactly. Yeah, that's the correct word. Yeah, how much weightage we need to pay or attention we need to pay to each and every word.
And most of it plays at the inference level, right, Prashant?
No, not inference level. Here at the attention score, when we are calculating, yes. Inference level also, that is what the probabilistic distribution will come out. That is something to do with the logics, but that we are going to discuss it later. But yes, at the inference level also, we are going to apply the softmax to find it out which of the word has the highest probability among all the tokens that are available.
so instead of one random weight vector, we are now using 3 random weight vectors QKV, so that we can get the attention of each and every word, calculating the score, attention score of each word.
Yeah, that is what they have came out the formula.
Yeah, this
Again, I know this is sounds something vague, but we need to stick to this formula because this is the formula which is used by all the LLMs which is available nowadays. So they come up with the formula with 3 different kind of a metrics which they came out, and they said that this will help us to figure it out the attention score.
Got it. Got it. So can I relate it like this? See, because when I read a lot of other articles, y is equal to mx plus c, right? So m is what the random weight vector we choose. So
Yes, we are going to discuss this in next few minutes about those things. So if you can just wait for 5-10 minutes, we are going to discuss those things.
Sure.
Any other question? Okay. Just in the interest of time, let's look at the other part, which is called feed forward network. Okay. And the main idea here is called this gig loop. Okay. And this is to introduce something called non-linearity. And what Saujanya has asked, that's what I'm going to come here in next few minutes. Any one of you understand what is non-linearity in dataset? What do you mean by non-linearity?
not a straight line,
Yes. And why do we need that?
because output can be in any form, right? I think
Exactly.
when you design a model, it can, if you plot in any XY coordinate system, when you connect all the dots, it can be in any form.
Yes, absolutely. So let's take this simple example, right? And I think I have showed this example earlier to some of the you folks, that in this case, if I need to separate between these circles, these red circles with blue circles, if I'm going to draw the linear line, right, like this, there is no way, there is no way. If I change it to this like this, change it to this like this, there is no way I will be able to separate these two values. So if I'm going to introduce linearity, I'm going to discuss this with the help of an example also. But if you look at this whole image, there's if I'm going to draw the linear line by any way, there is no way I can separate these blue blocks from red blocks. I need to introduce some kind of a non-linearity, right? So this is not a perfect image, but if I'm going to draw it like this to this, then I'm going to introduce the non-linearity, right? And the real world data, we know, always know it's a kind of a messy. It is always a non-linear thing. So I always use one example, which I'm going to show you, is that this is what this is going to do. This is going to draw a linear line where X is the input and W is the weight and bias. And we are going to initialize this weight and biases randomly. And again, the same thing which we have discussed so far, that we want the neural network to learn and update these weights and biases, right? So simple example I always gave is the number of hours and student grade, right? So let's say if student study for 2 hours, his grade will be 2. If he studied for 5 hours, his grade will be 5. And if he studied for 7 hours, and if his grade is coming as 6, that means in the simplest of scenario, and if we are drawing this linear line, his grade need to be 7. As simple as that. So what it is going to happen, that if our model is giving us output as 7 and 6, sorry, and the output need to be 7, then this difference in 7 and 6, that is considered as a loss, right? So what exactly is going to happen, that this loss is calculated, then the back propagation is going to happen, optimizer is going to run, and it's going to update these weights, update the weights at different layer, just to make sure that next time I'm going to ask, our prediction is going to be correct. So that is a linear layer which we are going to draw. So this is something like this. Something like this linear layer. So if I'm going to talk about 8 hours, its grade need to be 8. But here is the point, that we know that the real world use cases does not work like this. There may be a cases, if a student is studying for 5 hours, his grade may come out as a 2, right? There will be a n number of factors, or the vice versa. If a student is studying for 2 hours, his grade may be 5, right? So these are all the real world data set we have, and those cannot be captured with this linear line. In the linear line, it is always been like, if a student is studying for more number of hours, his grade will always be high. We always need to capture some non-linearity in our data set. And that is the whole idea about these activation function, to capture the non-linearity in our data. So there are a bunch of activation functions which are available. And if you look at this image, these are all non-linear. It is trying to capture some kind of a non-linearity from our data set, right? Because we all know that the real world data set is not always a straight line. It's always been messy. So that is the whole idea. Now, what these guys have done in case of this feed forward network, and actually this idea came out from this paper itself, attention is all you need. And if you go here, this is what they have done. This is a formula that they have used, and that is the activation function they have used is called ReLU activation function. And what these guys have done, if you look at this line, D model equal to 512, and the inner layer has a dimensionality of 2048. So what do I mean? What do they mean by that? Or if I can show you here, like this inner layer, they kept the dimension equal to 512. But for these middle layer, they increase the dimension to 2048, which is 4 times of 5028. And then at the outer layer, let's say this is like a 3-layer neural network where we have this input layer, this is hidden layer, and let's say we have the output layer. For output layer, they reduce it back to 512. And at that mere inner layer, they applied something called activation function. So activation function they applied just to capture those non-linearity. The main idea is to increase the dimension, is to capture more feature out from our data set. So like I told you, the more you are going to tell me about some person, the more I am going to know about that person. So same thing they assume it's going to happen in case of the large language model also, that if you are going to project your data into a high dimension data set, you are going to extract more feature out of it. And when you are extracting those feature, you are going to apply the activation function, which is going to capture all the non-linearity. Again, the idea is because the real world data set is not always linear. The same example, like student studying for 3 hours, his grade will not always be in 3. It may be 2, it may be 10, right? Because that is how the real world data set works. So this is how they have done in the case of feed forward network. Again, this is my assumption that when they published this paper, they projected it into the 4 times. So if you see it over here, the D model is 512 and DFF, which is the inner layer, had a dimension of 2048. So they have come up with this idea. Rest of the world, they just copy paste it. So any model you are going to see it over here now, any model, I'm talking about Gamma, Llama, whatever which is available and we know about it. I'm not going to talk about Anthropic and OpenAI internal model, but whatever the open weight or open source model they are available, they all are doing the exactly same thing. They are projecting 4 times whatever the dimension that is present, and the idea is to capture the more feature out of the data set and to increase the non-linearity. Is this part is clear to you guys? It is the simple one, but if you look at here, that let's say I have 512, right? And the inner layer has 4 times of 512, right? Then what I'm doing, this 4 into 512, I'm projecting it back to the 512, right? This is what these guys have suggested. So if we are going to calculate this, what will be the parameter size is 512 multiplied by, so okay, let's do the calculator. So 4 multiplied by 512, right? 2048 multiplied by 512. This is for 1. So this is equal to 1 million parameter. And you know, the same calculation we need to do on the back, on the inner layer back to the output layer. So multiply by 2. So this came out as a 2 million parameter. Now here is the interesting point. This feed forward network apply to every layer. So in our use case, we have the 20 layer. Look at that. These are all the parameters that is being occupied by the model. So in your use case, if you have a 512 dimension of your model, in our use case, we have a small dimension. I think we are using what? Where did we specify? So we are specifying 384 dimension. But in case if you have 512 as a dimension, that means 41 million parameter. And that is one of the interview question which has been asked, like for all these layers, which of the layer has the going to occupy the maximum number of parameter? And the answer is this feed forward layer, because here we are projecting it 4 times the number of dimension. So this is like more than 50 or 60%. I mean, let's do the calculation for our model. And just for the sake of simplicity, I have not projected into 4 times. I just projected into 3 times. And only reason for that is that I want it to run on the T4 and all those GPU. If you really want to try it, you can make it 384 multiplied by 4, right? 384 multiplied by 4. But that is going to increase my number of parameter. So what we can do, if we are going to do with this calculation, 384 multiplied by 384 multiplied by 2, because we need to calculate it, 2179 multiplied by 20, 23 million parameter. So if we are building, okay, let's do it for our model itself, 384 multiplied by 3 times, because I have done it for 3 times, multiply by 384 and then multiply by 2 into 20. So out of this 35 million parameter model, 17 million parameter is only present on the feed forward layer. So it's almost close to half of the model parameter. This is the layer which is occupying the most number of parameters. Please remember that, because this is one of the most popular interview question, which layer occupied the most number of parameters? And then the answer is feed forward layer. Is this part is clear? Again, we are going to do all these calculation tomorrow. Once I'm going to explain all of the different steps which is involved as a part of a model calculation, because feed forward is one of the layer we need to calculate the parameter. Wherever we have the trainable parameter, we need to calculate that, and we are going to sum all of those, and that will come out as a 35 million. But is this point is clear to you guys? Again, why we are doing it? Because this came out from this original paper itself, the 4 times, and rest of the world they have just copied it. So we are just following that trend. Any question or doubt so far? Okay. So let's look at the code, and then the code part is pretty simple if you understand this idea. Is that we have 3 layers where we have the inner embedding dimension and the hidden dimension. And the embedding dimension, we have seen it over here, is this one, 384, and the hidden dimension is 1152. This I'm again repeating, I multiplied 3 times. I'm not following the standard because I just want it to run on T4 GPU. If you want to test it, just multiply it with 384 with 4 times, and then you will be able to replicate the real world use case also. And once we have done that, only thing we are doing is we are applying the JLU function. And JLU function is just to capture the non-linearity in our data set. That's it. Once we done all those things, we will come up to the step 7. And I promise I will stop at this point, because I don't want you to overflow with the amount of a data or the idea that I'm throwing it to you guys. Transformer function is pretty simple. If you look at this image itself, what exactly we are doing in the transformer function? We have the RMS norm, which we have defined earlier for normalization. We defined the attention mechanism, then the bunch of RMS norm blocks, then the feed forward network. And there's one thing called shortcut connection, which we are going to talk in next 1 minute. The basic idea is to assemble all of these things. There's nothing special we are doing in the transformer block. So if you look at the transformer block, we have defined the attention mechanism, we have defined the feed forward layer, the input layer, all the normalization layer, we have defined it over here. There's one special thing which we have defined, is called per layer embedding. I have not talked about it, but I'm going to discuss it tomorrow. But this transformer block is all about combining all these layers together. Nothing else. We are not defining anything special over here, except for this PLE block, which I have not talked about it. And there's one more thing which is called a shortcut connection. Any one of you aware of this? What is shortcut connection or skip connection? Anyone has any idea?
For hiding a mask.
Not exactly. No, not for shortcut or skip connection.
To feed the output of layers to further layers ahead of, like, not sequentially, but actually do it in a like quicker way.
Yeah. So just to enhance what Sharjul has said, that the main idea of skip connection, like it's a kind of an older concept from the neural network, is that if you see it over here, that we have spoke about this whole workflow where we are feeding this embedding layer to the RMS norm and then to our attention mechanism. But the main idea is, and if you're going to read the older blocks and everything, skip connection is one of the older concept. And if you look at most of the neural network which is failed during the 1980s, is because if you are going to feed the data, I'm just talking in terms of current time right now, that let's say if you feed this embedding data to the model right now or to a transformer block, let's say all these weights become too small after it came out from this layer. Okay. So in that condition, if it's become too small, we can completely skip those steps for those weights, and we can have the alternative path so that we can try to avoid the vanishing gradient problem. Again, think of that perspective. The main idea for us is to have the training stability. And how we can introduce the training stability is we don't want our weights to become too small or too large. So for all the weights, if let's say there are some of the weights which after coming out from this embedding layer and we pass it to the RMS norm, we calculate the attention score, it came out from the RMS norm, it become too small that we can run out into the problem of vanishing gradient for those weights. So what we are doing for those weights, we can have the alternative path. And that alternative path, we are going to feed it to the other layers. That is the whole idea about the skip connection, nothing else. To have training stability and to avoid those vanishing gradient kind of a problem. So I know we have been in this training or workshop from last 2.5 hours. So I will stop at this point. Tomorrow we will start with this gamma model, or let me start from this point, step 9, where we will start the training. And then we will go backward and I will show you where exactly those model configurations are defined. But again, tomorrow training is also going to be 2.5 hours. It's much more than that. But we will start with step number 9 to initiate the model. Then I will go back to the step number 8 to show you where exactly those are being called. And we will perform up to the step number 12 to finish the training tomorrow. But my request to you guys, at least please try to run this Google Colab runbook, which will give you the idea how the training is being performed at various steps. And if you don't want to do it on the T4 GPU, and if you have your own Mac system, try to run it on your Mac. It is going to take like 7 hours to finish this training. So you need to be patient, but trust me, like whatever I have talked today, you will able to visualize all those concepts. So yeah, I will stop talking at this point. Any question?
So this positional embedding